Let's move on to the mini lesson of today. So here we're going to talk about more than two categories, sometimes also called distinguishable permutations. So here we define n choose k as the number of ways of picking k objects out of n. To motivate the next generalization, we would like to observe that n choose k is also the number of ways we can divide n objects into two groups. The first one with k objects and the second with n minus k objects. And here's what this part is saying. Basically, n choose k is equal to n factorial over k factorial times n minus k factorial. Another way you can think about this is that this numerator is being divided into two groups, k factorial and n minus k factorial. So let's connect this observation with the following example. So we have a house with 12 rooms and we want to paint 4 yellow, 3 purple, and 5 red. And how many ways can this be done? So here we have a situation where we have 12 rooms, and these 12 rooms, we want to divide them amongst a group of yellow, a group of purple, and red. One way we can do this is by first choosing 4 rooms out of the 12 to be yellow, and then out of the ones that remain, we choose purple, and then out of the ones that remain, we choose to paint them in red. So here, let me do it so you can follow along. And I drew these placeholders to aid me in the explanation. So for yellow, I have 12 rooms, and I want 4 of them. I want to choose 4 of them to be yellow. Once I'm done with this part, right here, once I paint 4 of my rooms in yellow, it should be obvious that now I have 8 rooms remaining, and out of those 8 rooms, now I want to paint 3 of them purple. So we get 8 choose 3 possibilities. Now, once I finish painting my 3 rooms in purple, it should be obvious that we now only have 5 rooms remaining. And out of those 5 rooms, I want to paint 5 in red. So that's all of them now. So we get 5 choose 5. And using the counting principle, in order to get all of the possibilities in which this can be done, I just take the product of all these 3 combinations. Once you do all of the algebra here, and I'll spare you from doing all of that, you should get a total of 20,720. However, there is an alternative, and we can generalize the alternative so we can avoid doing this messy computation. Alternatively, a second way of looking at the problem, which gives the last answer directly, is to first decide the order in which the rooms will be painted, and that can be done in 12 factorial ways. So here's what I mean. In order to calculate this problem, I'm going to first calculate the number of permutations. So going back to our problem, we can see that we have 12 rooms that we want to paint. Now, before I calculate the permutation, I should point out that here we don't really care about the order. Order should not matter because we just want to paint the rooms. We don't care which one gets painted yellow first. We don't care which one is painted purple second, or etc., etc. Now, the reason I'm calculating the permutations is because if I calculate the permutations, then I can divide by all of the repetitions. And I'll show you a strategic way in which we can do that. So again, let's pretend that we do care in which order these rooms are getting colored. So for the first room, let's say we have 12 choices in which we can decide to color the first room. After the first room is colored, then we only have 11 choices in which the second room can be colored. So on and so on. And here, the number of permutations is going to be 12 factorial. Now that we have the total number of 12 factorial permutations, we want to start getting rid of all of the repetitions. Once we get rid of all the repetitions, we're going to get all of the possibilities in which this can be done. And now I want to pay special attention to the colors of the rooms. So let's zoom in on yellow, and let's say that the first 4 rooms we're going to get colored in yellow. And then let's say that the next 3 rooms we're going to get colored in purple, and then let's say that the last 5 rooms were going to get colored in red. So here I've categorized these special rearrangements. So here we know that these 4 yellow rooms, we can rearrange these 4 in 4 factorial ways. And what this 4 factorial represents is the number of repetitions of this rearrangement. The same goes for the purple ones. Here we have 3 factorial rearrangements or repeats of this version right here. The same thing here. All of the repeats are going to be in 5 factorial ways. And using the multiplication rule, in order to calculate all the number of repeats, we can multiply the product of 4 factorial, 3 factorial, and 5 factorial. Hence, in order to do this problem, we have 12 factorial possible permutations. And in order to get rid of all of the repeats when we have more than one category, we can divide it by 4 factorial, 3 factorial, 5 factorial, and this will give you the same answer that we got before, that being 27,720. So now let's generalize this process, and here it is. For more than 2 categories or distinguishable permutation, the number of ways a group of n objects to be divided in subgroups where n1 are one type, n2 are a second type, all the way to your last type is n factorial over n sub 1 factorial all the way to n sub k factorial. And in our example, the n objects were the 12 rooms. The n sub 1 was the group of yellow, n sub 2 purple, and sub 3 red. And we used this formula in order to calculate the number of possible ways in which these 12 rooms could be colored in these 3 colors. Now, the formula may look a bit complicated, but I promise you that it's very easy to use. So let's take a look at some examples. And actually, I just noticed that on these examples, there was this 720. I couldn't see it, so that's why I didn't erase it, but that was not supposed to be there. So sorry for if you are confused with that 720 being there. So now let's talk about examples using this more than 2 category formula. So example 2. There are 12 students in the class. How many ways can a teacher give out 5 A's, 4 B's, 2 C's, and 1 F? And here's how we go about this. First, we get the number of students here, and we know that there's 12 permutations. There's 12 ways in which we can rearrange these students. It's 12 factorial. And now we can eliminate all repetitions by dividing by every category that we see. The 5 A's, so 5 factorial, 4 B's, 4 factorial, 2 C's, 2 factorial, and the 1 F, 1 factorial. Now to simplify this, I can expand 12 factorial. I'm going to expand it all the way down to 5, since 5 is the biggest one on my denominator. So I have 12 times 11, all the way down to 5 factorial. And now we can see that the 5 factorials are going to cancel out. So we can cross these out. And now we can multiply the numerator. So 12 times 11 times 10 times 9 times 8 times 7 times 6. And we're going to get a total of, I get a total of 3,991,680. And now as for the denominators, I expanded them. So 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 1 factorial can be simplified to just 1 times 1. So here, simplifying it even further, we get 24 times 2 times 1 on the denominator. And that simplifies to 48. So now we can divide by 48, and we're going to get a total of 83,160 possible ways in which a teacher can give out 5 A's, 4 B's, 2 C's, and 1 F to a group of 12 students. Let's try one more here. So now example 3, find the number of distinguishable permutations of the letters in the word Hoover High. To do this, we're first going to count all of the letters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 factorial rearrangements of those letters. Now to get rid of the repeats, we got to count the letters that were repeated. So here I notice that I have 2 O's. So that's going to contribute to 2 factorial because of the O's. And then we have 3 H's here. So that's going to contribute to a 3 factorial because of the H's. And I believe that's the only letters that are getting repeated. Each other letter is single. So we divide by 2 factorial and 3 factorial. 2 factorial coming from the O's, 3 factorial coming from the H's. So let's simplify this. I'm going to expand 10 factorial down to 3 since 3 is bigger than 2. So I'm going to get 10 times 9, 8, 7, times 6, times 5, times 4, times 3 factorial, all over 3 factorial times 2 factorial. The 3 factorials are going to cancel out. So here I'm going to get, 2 factorial is just 2 times 1, which is 2. And for my numerator, I'm going to get 604,800. So when we divide that by 2, we get 302,400. And that's the number of distinguishable permutations of the letters in the word Hoover High.